Welcome back to Advent of Code 2025. For today's problem, we have a bunch of devices, and each device has a directional connection to a list of other devices. So, for example, BBB with a colon followed by D and E means that the device B connects to D and E, and the first one outputs to all of the following ones. We're pretty sure that there isn't an issue with a specific device, but rather with a specific path. And data only flows through devices through its outputs, so this is directional. And we want to focus on the devices starting with the one next to us, so that is the one labeled U, and ending with the main output, which has the label out. So we want to find every path from U to out and determine the number of such paths. So how many different paths lead from U to out? So this is a directed acyclic graph. Though basically it's a graph because it has a bunch of nodes and edges connecting the nodes. It's directed because the edges are directional, as in they only connect from one node to the other, but not vice versa. And it's acyclic because there are no cycles. The reason we can assume there are no cycles is because nothing here mentions that we need to avoid cycles. It just says to find every path, and if there is a cycle in the graph, then the number of paths becomes infinite because you can take the cycle any number of times greater than or equal to 1. Now, technically speaking, it is possible to construct an example where there exists a cycle, but it doesn't exist on a path from U to out, such that you would basically get stuck in the cycle infinitely. So that would look something like that could look something like um, this, where the only path is here, and there exists an infinite loop that we can get caught in that can never reach O, and so it doesn't actually apply. Um, but that would be somewhat evil, and I made the assumption that it's a DAG, and that appears to work correctly. So I'm not going to bother implementing cycle detection just because I'm a bit lazy. Okay, so the input parsing today is fortunately not too hostile. We want to store a map from each node to all of its outputs. So for each line, we'll split it on the colon space. So source and destinations equals line.strip.split colon, and then graph source equals dests.split. And so that'll give us a map from each node to its outputs. And then we can define a function to count the number of paths from a given node to a given other node, so source and dest. And that count, if the source is equal to the dest, then there's exactly one path, which is the empty path. And otherwise, we'll simply sum the count from each output of source to the destination. So basically, in order to get from source to destination, we have to first make a step. So the first step will be this, and then the number of paths is just going to be the number of paths from each of those descendants to the destination um, for each of these. And it's possible to have a node with no children, so we do need to set a default case of the empty list in case this doesn't have any descendants and doesn't lead to out, in which case the sum would end up returning 0. And so we can just print the count from U to out. And as a further optimization, we should memoize the count function because let's say, for example, we have a situation where y has like 1000 paths to k, which then has 1000 paths to o. If we didn't memoize, we'd need to trace all 1 million of these paths separately. But with memoization, we know that k to o has 1000 paths. And then later on, each time we find a path from y to k, we don't need to count all 1000 paths from k to o. We can just immediately know that there are 1000 paths from k to o. So we may end up doing a lot of duplicate computation. So by using functools cache, we can save the result of each source and destination pair and that means that we avoid this computation the next time we call count with the same function. This is very useful for recursive functions where the broken down problems will often result in duplicates. Now, for the first part of today's problem, that actually doesn't end up mattering too much. So if we time this, we see that we get the answer for part one in less than 50 milliseconds. And if I remove the cache, then it takes just about the same amount of time. It's actually slightly faster, which could just be a fluke, but it is also very possible that it's just going to be faster because if you never run into a cache hit, as in if you never run into a duplicate computation, then saving stuff to a cache will just waste time. Because if you're only writing to the cache and never reading, you're never actually saving any time by using the cache, you're just wasting time building it in the first place. But it seems like it's just variance, so it doesn't appear to make a difference. For part two, our analysis has shown us that the problematic data path passes through the digital analog converter, which is represented as the DAC label, and the fast Fourier transform device, which is represented as FFT. We're not sure what the specific path is that is problematic, so we need to find every path from the server rack, which is SVR, to our output. So basically, SVR is a node that's always existed in this graph, and it's just AOC's way of not changing the input, but changing this problem specifications nonetheless. We now need to find all paths that visit both the DAC and the FFT in either order. So for example, from SVR to out, we have a bunch of paths, but only two of them go through both the FFT and the DAC. Okay, so we can keep our input processing. We can actually keep everything except the last line. And in order to go from SVR to out, passing through DAC and FFT, we could enumerate every path from SVR to out and then filter through them. But you may notice that there is a somewhat large number of paths, and we can't exactly iterate through all of them. One observation we can make is that the number of paths from A to B to C is equal to the number of paths from A to B times the number of paths from B to C. And this is because we are in a DAG, and so we'll never be able to go through the same node twice because that would be a cycle, which we are guaranteed not to have because it's an acyclic graph. And so this section will always be distinct and disjoint from this section, save for the singular node in the middle. And so we are basically just combining possibilities that are completely independent. And so we can just multiply the numbers together. And so if we're trying to go from A to the DAC to the FFT to B, or from A to the FFT to the DAC to B, then we can simply break these down into a product of three different path counts. And it turns out that that's actually extremely simple. So we'll take the count from the server to the DAC times the count from the DAC to the FFT times the count from the FFT to out, and then add that to the other direction. So we'll do something like this. And we see that that's basically instant because although this would make a lot of duplicate computations, we've avoided doing all of those with the cache. If we remove this cache, then this will never complete because we need to compute a result at least this many times without a cache, but with a cache, it runs instantaneously. In fact, it's running faster than part one, which is 100% a fluke, but yeah. Now, one optimization we could make here that I will mention is that recall that the graph is acyclic, which means that we cannot have a situation where there exists a path from the DAC to the FFT and also a path from the FFT to the DAC. And so only one of these can be non-zero. which means that theoretically we can pre-compute this value, and then if it's 0, we compute this, and if it's non-zero, we compute this. And this technically does avoid us making unnecessary computations. Um, and so what we could do is express it like so. So this would work as well. Um, but it's not really necessary, and this does require a bit more convincing to see why it's correct, whereas implementing it like this is not even slightly slower. So ultimately, I think I'm going to go with uploading this version, but it is an interesting observation to make that because of the acyclical nature of the graph, only one of these two values can ever be non-zero. So definitely a substantial difference in difficulty from day 10. I do like that this problem doesn't require using any libraries. I guess technically functools cache is a library, but it's in the standard lib, and you could just as well make this cache yourself, so I don't really count that. But in any case, thank you for watching, and I'll see you tomorrow for the, I guess it would be the finale of this year, as we only have 12 problems this year. So yeah, see you tomorrow.